The task library, one of Roblox Studios' greatest features, and yet it could be likely one of the most misunderstood. For example, do you really know the difference in behavior between task.spawn and task.defer? What about task.delay and task.defer? If you're not sure, do not fret. We're going to take a look at how the task library works and how Luau code is executed every single frame by the engine's task scheduler. And by the end of this video, hopefully you can walk away a little more confident when you're working with the task library and the run service. But before we dive into the task library, let's dive into our sponsor, Brilliant. If you're like me, always looking for ways to deepen your skill sets and make yourself smarter every single day, then Brilliant is your go-to platform for mastering many complex subjects such as math, science, programming, data analysis, and even artificial intelligence, with thousands of interactive lessons designed to make sure you actually retain what you learn. In fact, learning interactively has been proven to be much more effective than simply watching a lecture video. And plus, by working hands-on, you're building strong, critical thinking skills through experimentation and problem solving. Some of the most crucial skills to have when game developing are math skills, such as understanding linear algebra. It's one of the core mathematical principles for game development, and Brilliant offers many interactive lessons to help you hone in your linear algebra skills and use those skills in game engines, like Roblox Studio. So if you're like, heck yeah, I want to improve my math skills, then head over to brilliant.org/crusherfire to sign up and get 30 days absolutely free. You can scan the QR code on screen or check out the link in the description or pinned comment. You also get 20% off an annual premium subscription. Thank you to Brilliant for sponsoring this video. Alright, so let's see what exactly the task library is. And according to the Roblox documentation, the task library allows for functions and threads, which are coroutines, to be scheduled with the task scheduler. The functions available in this library generally support functions and threads. In most cases, using a function is sufficient, but for more advanced cases, it's recommended you familiarize yourself with the coroutine library. So there you go. There's your concise, simple definition of what the task library is built for. It's for resuming or executing functions or resuming coroutines. So if you want to create a brand new coroutine, give the functions another function, or if you want to resume a coroutine, give it an already existing coroutine. So let's look at one of the first ones here, which is task.spawn. So it says, this function accepts a function or a thread and calls/resumes it immediately through the engine scheduler. Arguments after the first are sent to the function/thread. So the purpose of this function is that it takes a function or it takes a thread and then it resumes it or executes it immediately. Right away. There's no yielding, there's no nothing. It creates the coroutine or executes the function. There's no yielding happening. So if we take a look here with our script, here we're spawning a function in a brand new coroutine, task.spawn this function, and it's just going to print out a message into the console. So let's ignore these for now. I'm just going to comment these out. And then let's go ahead and print something like after. We're going to print this after we call task.spawn. So let's go ahead and see what order is going to be printed. Is this going to be printed first, or is this going to be printed first? Well, according to the definition, this code right here should get executed immediately. So let's find out. And as expected, there the code inside of the function being executed by task.spawn ran right away, and then we printed the print statement after calling task.spawn. So seems like the Roblox documentation is correct. This gets executed immediately, right away. Not only that, this function returns a thread or a coroutine. So we can store that in a variable, we'll call it thread, and we can actually print out this thread to see its unique identifier, and we can prove that this thread or this coroutine is actually different from the coroutine that's executing the code in this script. So to get the coroutine that's executing the code in this script, let's go ahead and make another variable up here, we'll call it running, and that's going to be equal to coroutine.running, which returns the current running coroutine. And let's go ahead and just print out both of these. So we're going to print out the thread and running. Let's go ahead and play the game. As you can see, if we look at the unique identifiers of these coroutines, they are two completely different coroutines. And that's what we'd expect, right? Task.spawn is supposed to create a brand new coroutine for us. Or if we give it a coroutine, it'll take that coroutine and resume it for us. Now you might be wondering, what the heck's the use of creating another coroutine? And well, if you don't know much about the coroutine library, the purpose of creating a brand new coroutine is to allow us to, let's say, execute maybe some kind of other asynchronous operation without halting the thread that's currently going through and executing the code in here. So like as an example, I'm just going to pull in a random service like the player service, because the player service has some functions in it that need to make web requests. I think that get humanoid description from user ID might be one of those functions, or another one right here, get name from user ID async. What this has to do is it has to send a web request, and that means it's going to halt or yield the current executing coroutine. Now, let's say we want to get a name from a user ID, but we want this to be executing and doing its own thing. We don't want the code that's running through our script to be halted by this function call. And that's what task.spawn is for. You can spawn a function. Here's a brand new coroutine. And instead of this coroutine getting paused, this one created by task.spawn is the one getting paused. So that's why task.spawn can be quite useful. All right, how about this next function here? Task.defer. What the heck is this one? Well, it says it also accepts a function or a thread and defers it until the end of the current resumption cycle, at which point it is resumed with the engine scheduler, like with task.spawn. Now you might be wondering, what the heck does that mean? Defers it until the end of the current resumption cycle. What is that? Well, to understand what this is, we need to refer to the task scheduler documentation to see how Luau code is executed every single frame. So here we are in the documentation for the task scheduler, and the Roblox documentation states the task scheduler coordinates tasks done each frame as the game runs, even when the game is paused. These tasks include detecting player input, animating characters, updating the physics simulation, and resuming scripts that are in a task.wait state. So you might already know that a game is built up of a bunch of frames executing really fast, and a frame is a unit of game logic where work is done. Each frame should perform tasks efficiently, leading to more frames per second and a smoother player experience. So let's go ahead and figure out what the heck makes up a frame. And if we scroll down here, we can kind of see this graph that describes to us what's happening every single frame that runs in the game. So the first thing that happens is that we listen to any inputs or process any input events. So anything in your game, specifically probably local scripts that are listening to player input, those are going to get executed during this input stage. The next part of the frame is going to be rendering. But before we render it, there is going to be a pre-render event, or otherwise known as render step. And that is known as an invocation point. This right here is an invocation point. This is an invocation point. Same thing with other events that make up a frame. For example, there's events called pre-animation, pre-simulation, post-simulation, heartbeat. All of these are known as invocation points or resumption points where Luau code is executing or gets executed. Every single one of these invocation points can be thought of as a resumption cycle because it's resuming or executing code. And because the documentation here says that it defers it until the end of the current resumption cycle, this function is dependent on where it is executing in the current frame. For example, if we were to call the task.defer function while we're executing in heartbeat, it's going to push it or yield that function from executing until the very end of heartbeat. You can imagine that there's kind of like a queue of tasks that need to be executed, or deferred tasks. Every single one of these invocation points has some kind of queue like that. So if we were to execute code maybe in post simulation and we were to call task.defer, it's not going to execute it right away. It's kind of going to push it towards the end of this resumption cycle. So this is a resumption cycle, this is a resumption cycle, this is a resumption cycle, and so on and so forth. So to demonstrate that here in Studio, let's go ahead and forget this code up here because I'm no longer interested in it. And let's go ahead and take a look at task.defer. So let me uncomment this and then comment that out. All right, here's task.defer. And to test this function out, let's go ahead and execute it or call this function in the heartbeat event. So that's why we've grabbed the run service up here. We're going to get the run service, and this contains all of the invocation points or the events that execute every single frame. So that's things such as render stepped, or we got pre-render in here, pre-animation, pre-simulation, there's post-simulation, and that kind of stuff. And then finally, at the end of the frame, there is heartbeat. So let's connect the function to this. And then inside of that function, we're going to take this code and place it inside of there. And this should print at the end of the resumption cycle for heartbeat. Now to kind of visualize this, what I want to do is I just want to do a bunch of garbage here. I'm going to have a for loop that executes like 1,000,000 times. And we're just going to do some nonsense math in here. It doesn't really matter. We can do I times I minus I plus I don't really know. We're just doing some garbage to waste computer resources. And then we want to see where exactly this code is being executed. And to do that, there's kind of a cool function in the debug library called profile begin. And we can start profiling this code. So I'm going to call this our heartbeat work. And after we do the 1,000,000 for loops iterations, we're going to go ahead and end this profile so that way we can see it in the micro profiler. So let's go ahead and hop into our game. All right, to open the micro profiler, we're going to hit Control F6. This is the micro profiler. It shows us how long every single frame in our game takes to execute. And to pause it, we're going to hit Control P. We've paused it. We get this new menu to pop up, and you might already see something right here. Look at that, we have our heartbeat work. So these are all our different frames. The frames are kind of segmented by these vertical gray lines. So this is a frame right here, this is a frame right here. And as you can see, here is our heartbeat event. And you're going to notice that inside of this heartbeat event, there's this section right here called deferred threads. So you can imagine this is the queue that I was talking about. And you can see that our heartbeat work got pushed to the end of this queue. There's some other stuff happening down here and whatnot. I think this is a bunch of internal Roblox script stuff. But as you can see, because we use task.defer within the heartbeat event, it pushed this functionality here towards the end of this resumption cycle of heartbeat. So that's why our heartbeat work showed up right here. It just deferred it a little bit later. So to understand the ordering of this and the difference between task.spawn and task.defer, let's go ahead and comment this code out here. And then let's bring this code back. And we're just going to print out task.spawn. We're going to print out after. But what we're also going to do is we're going to call task.defer up here. And we're going to print, whoa, task.defer. And I want you to sit here and look at this code real quick and imagine in your head, what's going to be the order of these things appearing in the console? Is this one going to print and then this one and then this one? Or is this one going to print and then this one and then this one? Keep it in your head. We're going to play test and see what the ordering is. So we're going to hit play. And here's the order. Task.spawn executed first, then our print statement with after in it, and then finally task.defer executed just a little bit later. So let's go ahead and go back to the code. So this executed first, then this executed, and then finally up here, this one executed. And that makes sense. This is the only function right here that is yielding this code. It's yielding it, it's pushing it to the end of the current resumption cycle. So that's why it executes just a little bit later. All right, I've got one more scenario here I'd like us to sit here and think through. So we have the same setup, but this time I added a task.wait call. We're going to look at this function in just a second, but basically what this does is that as a TLDR, this function halts the current executing coroutine. So this is going to get executed and then it's going to hit this. The coroutine is going to yield until the next heartbeat, and then this one's going to execute. So take a look at this. What do you think the order of the print statements are going to be? We already saw that it would print this, this, and then this, but now that I've inserted this in here, how is it going to print? Is it going to print this, and then it's going to print this, and then it's going to print this, and then it's going to print this? Well, let's run the game. And as you can see, we get task.spawn, we get after, then we get task.defer, and then we get after wait. So basically with task.spawn here, it's going to go through and execute all of the code in this function until it hits a yield, which is right here, or task.spawn ends. And then once it hits a yield or it ends, then we print after, and then after this finishes executing, whenever this gets resumed, then that's what gets printed right here. The documentation states that this function should be used when a similar behavior to task.spawn is desirable, but the thread does not need to run immediately. So basically, most of the time, you should be using task.defer because it allows you to work with the engine's task scheduler to properly schedule tasks to execute in an order, in a predictable order that you want. Because for example, if I had, let's say, 3 calls to task.defer here, this first call is going to push this coroutine or this thread to the end of the current resumption cycle, and then this one's going to do the same thing, and then this one's going to do the exact same thing. So if all of this code right here was to execute, this would execute first, then this one, and then this one would execute, and then this one would execute, and then this one would execute because they get put in a queue. All right, how about task.delay? What does this one do? Let's read. It says it accepts a function or thread and schedules it to be called / resumed on the next heartbeat after the given amount of times in seconds has elapsed. So we can give this function a duration, and this basically says how long do we want to yield or wait for before we execute the function or the thread that we give to task.delay. So back inside of Studio, let's go ahead and get rid of this code up here, and let's go and visit our beautiful, beautiful task.delay function. So here you can see that I'm passing an argument of 0 seconds to task.delay. We'll get to that in a moment, but let's go ahead and delay this for 1 second. And then to observe actually how long this function right here was delayed for, let's go ahead and grab the timestamp before we call task.delay. So we could call this first timestamp, and it's going to be equal to os.clock. You could also just call it timestamp, whatever. And then inside of task.delay, we're going to actually observe how long this function or this code got delayed for, and we can do that by getting the current time by calling os.clock again and simply subtracting it from the last timestamp, so we can see just how long the function yielded for, because it's not going to be absolutely perfect to 1 second, but it's going to be pretty gosh darn close. As you can see, it was delayed for 1 second, or approximately 1.0012308 and so on seconds. I mean, basically 1 second. It was pretty close. And then our code executed. So as you can see, the purpose of task.delay, as the name suggests, is to delay a function or a thread from executing for the duration that you pass. Now here's some interesting behavior with task.delay. What if we pass 0 here, right? Well, let's go back to the documentation. The documentation says it is scheduled to be resumed on the next heartbeat after the given amount of time in seconds has passed. So if we give it 0, it's going to say right here, providing a duration of 0 will guarantee that the function is called on the very next heartbeat. That's kind of interesting behavior, right? The very next heartbeat. If we go back to how a frame is structured inside of this diagram here, let's say we call task.delay with an argument of 0 seconds in, let's say, the pre-render or render stepped event. Well, when is that code going to execute? According to the documentation, it's going to run at the next heartbeat, which is right down here. So it's actually going to execute the code in the same frame. But if we were to call task.delay with an argument of 0 seconds within heartbeat, then it's going to wait until, the next heartbeat, which is at the next frame. So it's going to depend on when you call task.delay of where it's going to execute, what heartbeat it's going to execute at. So let's go ahead and test out and see if the documentation is lying to us or not. Let's go to the run service. Let's go to the render step event, and let's connect a function to this bad boy. Let's take this code, let's throw it in there, and we want to see when this code actually gets executed. So to display this, let's go ahead and make some more debug profiles. So we can do debug.profile begin. We'll call this render step. And we just kind of want to do a bunch of garbage again. So we'll do that. And then let's copy this and do the exact same thing within task.delay. We'll throw that in here, but instead we'll call this next heartbeat, because that's when this is supposed to execute, at the next heartbeat. All right, let's go and play test the game. Let's unpause the micro profiler, and then let's pause it again, and then I'm going to stop playtesting. And let's go ahead and take a look at one of these frames here. So if we scroll out, and let's see if we can find render step. Here we go. So here's pre-render or render step. And as you can see right here, we execute in deferred threads our code for render step. And then at the very next heartbeat, which is in the exact same frame, because mind you, this is one whole frame right here, then we get next heartbeat executed. Isn't that pretty cool? So we get render stepped, and then we get heartbeat. And to prove that this is actually the task.delay that got executed right in here, let's go back to our script, and let's actually properly identify this. Let's make a variable out here. We'll call it frames. And every single render step, we're just going to increment frames by 1, and then we're just going to kind of concatenate that with our string. So render step underscore what the current frame count is, and then we can copy this, do the same thing here, and we'll call this next heartbeat. or next underscore heartbeat, whatever. Okay, and then let me get rid of these print statements because they're kind of annoying. All right, that looks good. Let's play the game. Let's resume the micro profiler. Let's pause it again, and let's take a look at a frame here. So let's go all the way down. Here we go. We got render stepped on frame 94. And then if we go to the very next heartbeat, oh, look at that. Next heartbeat at frame 94. So the documentation didn't lie to us. Task.delay with an argument of 0 seconds resumes at the very next heartbeat. Let's go ahead and change this around and have this be the heartbeat event. And we're going to call this heartbeat. And then this one down here is going to be next heartbeat. And let's go ahead and play test the game. Unpause the micro profiler. Pause it again. And here we go. If we take a look here, actually we still have render step going on in here. I'm probably looking at the wrong frame. This is very interesting. I don't know why there's render step in here. Our code doesn't have any render step debug profiles. That's interesting. Okay, let's stop playtesting. Let's try that again. All right, double check. Right, heartbeat, next heartbeat. There's no render step debug profile in here. Okay, let's try this again. We're going to pause. There's still render step. What is happening? This must be a studio bug because look at the timer says render step, but the label says heartbeat. That's really weird. Okay, well, whatever. So if we take a look at just a heartbeat here, let's go to this one. This is heartbeat for frame number 69, and then this one right here is heartbeat number 70. And then if we go to the next heartbeat, which should be down here. There we go. Look at that. Actually, never mind. These labels are getting kind of confusing. Okay, this is not next heartbeat for frame number 69, and then this is next heartbeat frame number 70. So that means right here we have heartbeat for frame number 70, and then here we have the next heartbeat for frame number 70, and then this one is heartbeat 71. Yeah, wow, this is getting really confusing. Look at that. Look at these labels. They are like totally incorrect. I'm getting confused. Must be a weird profile bug, or perhaps my code isn't correct here, but I mean, my code looks all right, so I don't know what's up with that. Anyways, as you can see, right here we had heartbeat for frame 70 execute, and then here at the next frame in the next heartbeat, we had next heartbeat for frame 70 execute, and then here we had heartbeat for frame 71, and if we go to the next frame, here is the next heartbeat for frame 71. So as you can see, if we call task.delay with 0 second argument in heartbeat, this code is going to execute at the next frame. Now, how about everybody's favorite function in the Roblox API? Task.wait. What does this do? Well, it yields the current thread until the given duration in seconds has elapsed, then resumes the thread on the next heartbeat step. So basically, task.wait is almost like task.delay, but whereas task.delay resumes or creates a new coroutine, like a separate, different coroutine, task.wait does the same thing on the current coroutine that's executing task.wait. So if we come back here into Roblox Studio, we should be able to get the exact same behavior that we have going on right here, but instead of calling task.delay, what we can simply do is we can call task.wait, and then we can come down here, take this code, get rid of task.delay, get out of here, and we can put this code down here, and this should have the exact same behavior. Why? Well, because we're not passing any arguments to task.wait. This is basically 0 seconds. So this should be the exact same thing as task.delay. So if we go and we playtest the game here, open up the micro profiler, pause it, and we take a look at the labels here that are still very, very confusing. We should have, here we go, heartbeat for frame 130. And if we go to this one down here, here we go. Here we have the next heartbeat for frame 130 in a, different frame, right? Because we used task.wait, it resumed it at the next heartbeat. And because of that, if we were to actually swap this to render step and switch this to render step, this code right here is going to execute in the exact same frame because, again, this function is waiting for the next heartbeat. So if we play the game, pause it, let's find render step. Here we go. This is for frame 89, render step 89, and then we call task.wait, and then it gets resumed right here, next heartbeat at frame 89. This is within the same frame. And of course, just like task.delay, you can pass any duration you want in here. If you want to wait 100 seconds, you want to wait 1,000 seconds, you can do that, and it will resume the code roughly at about the 1,000 second mark, give or take like a couple milliseconds. Now the final function we're going to take a look at here is task.cancel, and it says it cancels a thread and closes it, preventing it from being resumed manually or by the task scheduler. So let's say in their example here, you had a function or a coroutine being delayed by 5 seconds, but at some point in the future, you're like, hey, you know what? I don't need this thread anymore. Maybe you're cleaning up something, or you just don't care about this code. You don't need it anymore. Well, you can task.cancel it, and the code inside of here won't execute. So let's go ahead and do that. Let's create a variable called thread. And for this example, let's use task.defer. So we're deferring it or yielding this function from executing till the end of the current resumption cycle. And we're just going to print, task.defer. But down here, let's just say for some reason we're like, oh, you know what? I don't want this thread anymore. We're gonna cancel it. And then we're going to print after cancellation. And then let's go ahead and actually observe the state of this thread. So let's go ahead and print right here. We're going to print coroutine.status of this thread. And it's going to tell us whether or not this coroutine is dead, normal, running, or suspended. And then we cancel it, right? And then we're going to print the status again. So right here, this should get printed that it is suspended, and then after we cancel it right here, this should print that it is dead. So let's play test the game and find out. Here we go, we get suspended printed, and then we cancel it, and now it's dead, and we print after cancellation. So there you go, that's task.cancel. It allows you to cancel coroutines. Now we do have a couple other functions here in the task library, which is task.synchronize and task.desynchronize. I'm not going to go over these functions because this is all about parallel Luau. If you want to learn about these functions, you can check out the video I made on parallel Luau. So go ahead, check it out. This is for sophisticated people. And if you want to be a sophisticated person, check out my video on it, all right? So that's basically the task library in a nutshell. It allows you to execute functions and threads and schedule them with the task scheduler. And we learned that the task scheduler resumes or executes a bunch of stuff every single frame, and a frame is built up of a bunch of different invocation points that Luau code runs. And each one of these invocation points is known as a resumption cycle or invocation cycle. And because we can use the task library to mess around with coroutines, we can defer coroutines to the end of a resumption cycle. We can wait for specific events like the heartbeat event, and we can access all of these invocation points within the run service. So as you can see in the run service documentation, we have a heartbeat event, a post simulation event, a pre-animation, pre-render, pre-simulation, render step. Whoa, they deprecated render step. Wow, and they deprecated step. Hold on, fellas, this is brand new news to me. I did not see that until now. That's crazy. Render step and step, they're gone. They're deprecated. So it looks like pre-simulation is the new stepped and pre-render is the new render step. But the question is, are they going to rename bind to render stepped and unbind from render stepped? What are they going to do with these functions? You can't really rename them, otherwise you're going to break a bunch of games. So are they going to make a couple new functions for specifically pre-render? Who knows? But it looks like for now, the 5 events we get is going to be pre-render, and then after that, pre-render, we're going to get pre-simulation, and then we get post-simulation, and then we get heartbeat. So these are all invocation points in the current frame that execute Luau code. So I hope you all enjoyed this video. I hope you're a little more confident with the task library and how it works and what you can use it for. And now you get to go out and mess around with it and make some code some stuff. Thanks for watching. I'll see you next time.